Hello and welcome to iitiansgateclasses once again. So today we will be solving some of the merge sort questions first. Then we will see more better sorting algorithm and some more basic sorting algorithm on which we can find some questions on various examinations. So sorting is very fundamental in algorithm where we have given an array of item or a list of item and we have to arrange them in increasing or decreasing order, right? So let's start with the merge sort questions. I have explained in previous lecture that how merge sort works, where we are given with the array of random elements, and first we basically split the array in half. Okay, then again the first half will be split into more granular array, and the second half will be split into 1/4 array. Okay, then again we will split it until we get two or one element. In our algorithm we have seen that, and we will split until we get one element. Then we apply merge algo from top to up. Okay, so if you check the tree like structure here we develop, where we explain how can this split array can be merged so that a single sorted array, we can find out a single sorted array. Okay, I think those part have been removed from the slides, but it's okay. Let me take an example again. On the basis of that, we will solve some gate questions also. Okay, so let's see that an example of an array where we have initially we have 25, 15, 68, 42, 91 and 77. So we have these many elements. Okay, 25, 15, 68, 42, 91. So we will split it into two parts. Here we have 25, 15, 68 only, and on another one we have. We'll try to split into exactly two half. If the number of elements are even, then it's okay. If it's odd, we can put the one extra element either on the left side or right side. It doesn't really matter. For example, if you see here, it's 25, 15 we put on the left side and 68 on the right side. 42, 91, and here we have 77. Again, we will split it 25, 15, and it's 68 only. It's 42, 91. Now, once we split each array, so that in the array we only have single element, we will apply a merge algorithm. So in the merge algo, we will see that at each node we have this. We consider this as a sorted array. We consider this as a sorted array because as we have a single element can be considered as a sorted array. If array have only one element, that element is sorted. Okay, then we apply the merge algorithm. Okay, I explained merge algorithm very well in the last lecture, as you can see. And once the merge algorithm is applied, we input this one and the output will be 15 and 25. Okay, 15 and 25. These two will be merged into a single sorted array. These two are independent sorted array. This is independent sorted array. Okay, this is also independent sorted array, and we merge these two independent sorted array into a single sorted array using merge algo. And merge algo required order of n, where n is equal to number of element in final sorted array. Okay, and why it's order of n? Because we are using outplace algo. Outplace algo means we are using a extra space to merge these two. Okay, so it will have 25 here, 15 here. We will have a extra space of size 2 because this is size 1, this is size 1, and P will be placed here, Q will be placed here. We will compare P with Q. Okay, so Q is smaller, it will be placed here. So Q will increase, Q will value increase to 2. Now it's greater than size of this array and we place 25 here as it is. This is the single sorted array. Okay. So then we will merge this one and this one. Ultimately, we'll get here 15, 25, and 68. Similarly, here we apply the merge algo on these two. We will have 42 and 91 here. And we will apply merge algo on this one and this one. We will have 42, 77, and 91. Why am I solving this one? Because sometimes they give you an array in examination and they will tell you that at level 1, so if this is level 0 and this is level 1, at level 1, what all array I am getting? At level 1, what all array I will get? So the answer is 15, 25, 90, 68. This is array 1 and array 2 is 42, 77, and 91. Okay, once I merge these two, I will have a final array 15, 25, 42, 68, 77, and 91. So this is our final array. They will not ask you array at level 0 because that is just single sorted array, but they can ask you at level 1 or 2 or 3 what all array you have using merge algo, right? So this is how you can apply merge sort using merge algorithm. Okay, the core of merge sort is merge algorithm, which takes order of n time, and here we have log n level. So total time complexity is n log n. Okay, total time complexity is n log n. Now let's move on to one more question where we are given with a very generic parameters, something like the input is given that in the question it is mentioned that the input is in form of log n sorted arrays. Okay, it is given that the array size is equal to n, and we have log n sorted array. Log n already sorted log n array we have, right? So how many array we have? Number of what is the size of single sorted array? What is the size of single sorted array? It is given that size of each array is equal to n by log n, right? Now these three things are given. That we have log n sorted array, size of whole array is n, size of each array is n by log n, right? So we need to find time complexity. We need to find the time complexity when time complexity of sorting. Okay. Time complexity of sorting. Like how much time will it take to sort these arrays where we are given log n. This is the number of arrays. Okay. Number of arrays are log n. Size of each array is n by log n. Okay, and these are already sorted. We need to merge these sorted arrays, log n sorted arrays. Number of arrays are log n. Size of each array is n log n. Now, what is the time complexity to basically merge these algo into a single sorted array? Okay, we want a single sorted array. How much time will it take? Let's start. So at the bottom level, we have an array of size log n, another array of size log n and log n, another array of size n log n, till log n, number of arrays are log n, okay, and log n, right, and log n. So these are single arrays. This is one array, this is second array, this is third array, this is some log n minus one array, nth array. Okay, this is log nth array. Okay. Now we have to combine these to apply merge sort. Okay. So once we apply merge sort on these two, how much time merge sort will take? It will take 2n log n. Okay, and this is the size of resultant array. In the previous example, you have seen that the time complexity is order of n. Okay, and n is the number of element in final sorted array. Here, the final sorted array is of size n log n. Okay. Similarly, once we apply some merge sort here for these two arrays, like n log n, in third and fourth array, it will also take 2n log n. Similarly, here also it will take 2n log n. But what is the total effort here? What is the total effort? What is the total effort here? It is log n by log n. Okay, so that is order of n. Why log n by log n? Because why effort at each level, or you can say effort at the bottom level, is order of n? Because for each merge, it's taking 2n log n. For each merge, it will take 2n log n. And how many merging do we have? How many merging do we have? Log n by 2 merging we have. So you can calculate it like this. The effort at this level, effort to merge log n arrays of size n by log n, is basically log n by 2 multiplied by 2n log n, which is also order of n. So in the layman term, you can say that total element are n elements are there. Okay, n elements are there. So effort at this level to apply all the merge algo is basically n. So how can we calculate total effort or total time complexity? We just have to calculate all the levels, like number of level we have in this array. Okay, so how can we calculate number of arrays? Let's see that if we combine these two, it will become 4n log n. Right, here if we combine any of these two, it's 4n log n. Again, effort at this level will also be order of n. Effort at each level is order of n. Remember this. Why? Because total elements are of n. Once we combine these two, it will take 2n log n. Similarly, how many merge algo or combination we are doing? We are doing log n by 2 combination, log n by 2 merging. Okay, and at the end of the merging, we will be having an array of this size, this. So effort at this level is order of n. Similarly, effort at this level is also order of n. Using the same logic, total number of elements which are merging is order of n. Okay. Now at the root level, what's happening that we have 2n by log n elements. Okay. 2n log n, 2k log n. How 2k log n? Let me see this. N log n. This is the singular array size, n log n. This is singular array size. Similarly, we have n log n, n log n. Once we combine these two, we will have 2 power 1 n log n. So at the second last level, we have 2 power n log n. At the third last level, we have 2 raised to power 2 n log n. If you remember here, once we merge 2n log n and 2n log n, its sum 2n log n plus 2n log n will appear in a single node, which is basically 4n log n, which is equal to 2 raised to power 2 n log n. Okay. So at the root level, we will have 2 raised to power k multiplied by n log n. And what is the number of element at the root level? N. And k is the number of level. K is the number of level. Okay. We iterate this step k times. We iterate this merging step k times such that the last root node at the root node where root node have only one element. Okay, one node. That node contains n number of elements. And in the generic form, we have applied k times merging. We have applied k times merging. We have applied. So what is the value of k? Using this equation, we can find out the value of k. So ultimately, at each level, we know that the effort is order of n. Okay, at each level, the effort is order of n. Now our task is to find out number of levels. So using this equation, we can find out number of levels. How we achieve this equation? At root level, we applied this merging step k number of times. Okay, k number of times. So at the this is 2 raised to power 0. Okay, at the last level or leaf node, we have 2 raised to power n log n. At the second last, we have 2 raised to power 1 n log n. At third last, we have 2 raised to power 2 n log n. So at the kth level, or you can say that at the root level, if we apply this, if we repeat this step k number of times, we will have 2 raised to power k n log n, which is equal to n number of element. So 2 raised to power k log n, k is equal to log n. Okay, so what is the time complexity? It is at each level, number of level are log n, and at each level effort is n. So we multiply these two, it's n log n. Okay, so these kind of questions you can see in the examination. So let's see a much simpler question also. This is quite difficult. If you don't understand merge algorithm, you won't understand these questions. So try to understand merge algorithm first and try to solve simple examples first. So you are given with the array of 27, 15, 42, 19, 88, 14, 92, 68, 4 and 7. Okay. So they are saying that once we apply the merge sort, and we call merge sort function 2 times only, what is the output array? Okay, they're saying that we have applied merge sort only 2 times. So what is the output array? And they will give you some options. So like previous question, you can write it like this: 42, 19, 88, 14, 92, 68, 4 and 7. Let's combine these two. It will be 15, 27. It will be 19, 42. it will be 1488, it will be 6892. Okay, and this will be 4,7. So this is first pass. Now we combine these two. It's 15, 19, 25, 42. Okay, and this will be 14, 68, 88, and 92. And this will remain same because there is no other node to merge with it. So this is the second pass. This question is asked in gate. This question is also asked in gate. This question is also asked in gate. Okay. So this is the second pass. So output is this thing. This whole thing is the output. Okay. Now let's move on to the next algorithm, which is quite popular, Quicksort. This algorithm is given by Tony Hore. I think I'm not sure whether I'm spelling like pronunciating it right, but Tony Hore developed this algorithm, and he got Turing Award. What is Turing Award? It is the highest award for computer science research. Okay. I think he developed this in 1960 in Moscow. Okay, you can Google it also. So he got Turing Award. It means that this algo have something in it. So that's why in examination, mostly in gate examination, people can see many questions from Quicksort. Sometimes they get 2 questions also from Quicksort of number 2 and 1, something like that. In other examination also, Quicksort is quite popular. So what is the core of Quicksort? Let me try to explain it to you. The core of Quicksort is, by mistake, I stopped sharing. Sorry for that. So the core of Quicksort is partition algo. So in theory, what does partition algo says? It says that you can pick an element, any element, or any index of that array. For example, you are given with certain elements like 45, 68, 92, 78, 15, 25, 39, something like this. Okay. So I pick 45. For example, I picked 45. Generally, whatever algorithm, whatever type of Quicksort you see, there are various types of Quicksort. Generally, we pick the first element as the pivot element. Okay, I will tell you what pivot is. So whatever element you pick at the end of one pass, one partition algo, one pass of partition algo, this 45 will go to its place, wherever it belongs. And after 45, we will have all the elements which are greater than 45. And before 45, we will have all the elements which are lesser than 45. Okay. We will have all the elements which are greater than 45. These elements may be jumbled. Like these elements, these elements need not to be sorted. But all the elements will be less than 45. So 45 will get its place, and all the elements on the right side are also greater than 45. That's what partition algo does. So now we can solve this part separately and we can solve this part separately. There's no merging required. because all the elements on the right side are greater than 45, all the elements on the left side are less than 45. That's what partition algo does. Okay, let's write the algorithm first. Then we will move on to an example. So partition algo is something like, it's very like, you can look at the steps and you will know why we are doing those steps, why we are performing those steps. And this will result in something like this, right? Whichever element we pick, it will get its place. And we will have two problems in our hand, two smaller problems. That's what divide and conquer, right? We are dividing a bigger problem into smaller problems. And then we are conquering those problems. So let's see algorithm first. It says that partition, we are given with an array A, start index I, okay, and index J. So you are given an array from I to J. So we have to apply the partition algo on array I from index I to J, okay. So we say that, let's take the first number as a reference from which we will compare. Let's save it in x equal to A of I, like the previous one where we have taken 45 for the reference. And we will take a number for iteration, like P for comparison, right? Now we apply the iteration. You say that Q equal to I plus 1 and Q is less than equal to J Q plus plus, right? If I didn't provide the condition here. We say that if A of Q less than equal to X, we have taken this number as a reference, right? This number as a pivot. This is a pivot element. So each time we will try to compare the current looping element to this element only, okay? So we are comparing this iterating element Qth index element to this X. X is not index, X is the element, Q is the index, okay? So we say that if this is the case where X is less than Q, X is greater than Q, A of Q, then we will do P equal to P plus 1, okay? And we swap these two elements, A of P and A of Q. We will swap these two elements. This is the case. And at the end of loop, we will swap A of P, not A of P. I will swap A of I and A of I and A of P. Okay. So this, let me highlight the part separately. This is pivot selection. Okay. This part is basically splitting the array into two parts such that the ith element, these two. So let me put it in this way, that this is done for two purposes. One, to get actual place of I, because we have selected ith element as pivot, right? So this is to get actual place of ith element. And second, if ith element reaches here in the middle of somewhere, okay. So secondly, the purpose of this loop is that this all element are less than I and this all element are greater than ith element. So we have selected the first element, ith element as pivot, okay, and we finding out the position of pivot, okay, and using this algorithm, this is the core of Quicksort. You can note this down. We will run this algorithm using some examples, so you will have an understanding. Let's take an example. 45, 68, 92, 78, 15, 25, 39, 85. Sorry, let me write it as 55. Okay, 55. I will do two passes of Quicksort algorithm and we will see how it's doing. And 29. Okay. Now, these are the indexes. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are the indexes. So as per the algorithm, we selected a P as we initialize X as 45. Okay. Here we know that I is equal to 0, J is equal to 9. Okay. This array is given, I is equal to 0, J is 9. And I is equal to A of, X is equal to A of I, which is 45. So this is X, this is our X. And we assign P as I, which is 0. So this is where I lies and P lies. This is where J lies. Now we have to initialize Q in the loop as I plus 1. So this is Q. Okay. Now you can basically check this code. I will run the iteration. Okay. So what we are saying that if X is greater than equal to A of Q, right? Which is not true. So we won't do anything. P will remain the same. We won't do anything. We won't do any swapping. Now our Q will increase to this one. Again, we will check that A of Q is less than equal to X, or X is greater than equal to A of Q. This is not true. Again, this is not true for this also. Now, for fourth index, this is true. It means that A of Q, which is 15, is less than equal to 45. If this is the case, increase the value of P. increase the value of P, increase the value of P. P is initially 0, we increase the value of P. And swap these two, and swap A of P and A of Q. Let's swap these two. We need to swap these two. So 45, let me try to write it there only. The top of it, we will try to write it. Okay. At the bottom, we will move the pointers like P, Q, I, and J. And top, we will try to swap it. Okay. So these two will be swapped. 15 will be written here. 68 will be written here. Now we will again increase the value of Q. As loop is going on, it will go till J, right? It will go till J. We will again check if A of Q is less than X. So this is the reference point. We made this as a pivot element. It means that this is the reference point to which we will compare the Q again and again. And we will swap it with P until P reaches to its point where we have to put this 45. Okay. So once this Q is compared with this, we will increase the QP. Whenever this condition is satisfied, we will increase the value of P first, then we will swap. We will increase the value of P and we will try to swap these two. So it is 25 here, 92 here. Okay. Next iteration, Q is increased. And we see that 45 is again less than 39 also. So we'll have to swap these two also. We'll increase the value of P. P will come here. We'll increase the value of P. This is 39 and this is 78. Okay. Now let's check the next iteration. 45 is actually less than 55. So we don't care. We'll increase the size of Q. 45 is less than 106 also. We increase the size less than Q. Now, 45 is greater than 29. So we will first increase the value of P, which is here, and then we swap it. So this 68 will become 29, and this will become 68. Okay. Now P have reached till here. P have reached till here, and Q is reached here. So loop will end. This for loop will end, and we will swap the ith element which we have taken as a pivot with the current value of P. With the current value of P. So this is the optimal value, actual position of pivot, or you can say reference element. Okay, reference element. So this is the work of brilliant mind. Here at the end of loop, we will swap ith element with P element. I is 0 again. We haven't changed I or J. We are just moving P and Q. Okay, so this is P, this is I. We will swap these two. We'll swap these two. So here it becomes 29. Here it will become 45. Now let's write the array after first pass, first partition algorithm. It will look like 29, 15, 25, 39, 15, 25, 39, 45, 92, 78, 55, 106, and 68. Now check this one. Check this one out. These all elements are smaller than 45. These all elements are greater than 45. So this is the partition algorithm or partition method. We followed this algorithm and we reached to this part where 45 is here to its correct position. Now we don't have to touch this one, 45. We just have to touch this part and this part, right? We don't care about 45 now. Now, once we pick this one, 29, 15, 25, and 39. Let's apply again. Quicksort 29. There are 25, 39. So this is I. Initially, this is J. Okay. And initially, we initialize this one as P and this one as Q. If you see that, we initialize Q as I plus 1, P as I. Okay. Okay. Then we will try to apply this partition algo here on this sub array. On this sub array. Okay. So we have taken X equal to 29 and this is P, this is Q. We will compare the X with A of Q, which is lesser. Okay, which is lesser. See, A of Q is basically less than X. This condition is satisfied. So we will increase the value of P equal to P plus 1, and we try to swap. So P will, let me use red color, P will become here. And we swap this 15 with 15 only. We'll swap 15 with 15. So it will remain here. Now in again, the next loop, the value of Q will be increased. We will compare 29 to 25. So this is less, again less. So first we will increase the value of P, which is here. And we swap 25 with 25. 25 will remain there only. In the next loop, we will compare this X 29 with 39. Okay, so it is greater. This condition is not satisfied. 39 is greater. So this is the ideal value of P. And remember, once the iteration is done, once the partition algorithm for loop is done, this is the ideal position of the pivot element which we have taken. This is the reference element we have taken. So this is the ideal position of this one. So at the end of partition algorithm, we swap ith element with P. We haven't changed I. I is here only. We just swap these two, this one and this one, right? So at the end of partition algo, we will have 25, 15, 29, and 39. Okay, now see, 29 is at its position now. It have reached to its position, right? Here we only have single element, so we don't care. Now this thing we have to take care. Again, we apply the partition algorithm on this one. So we divide it like this. And we apply partition algorithm and partition algorithm. Once we apply the partition algorithm, we will have two partitions in our hand. Okay. If you see here, once we apply the partition algorithm, we have two partitions. If the partitions are of almost equal size, this is called best case. Best case for Quicksort. Quicksort. Where these two partitions are of almost equal size. Okay, this is the best case. Why? I can tell you why. Okay. So if this is the case, 1, 2, 3, 4, 5, 6, 7. If this is the case, we have taken this element as a reference element. After the partition algorithm is completed, where this element will be swapped to, it will remain here, here. So we have only one partition, this one, only one partition. Okay. So again, we will pick this element and we will apply partition algorithm. This element will remain here only. It won't change its position after partition algorithm. So we will have only one partition, this partition. Again, we will apply the partition algorithm. This element will remain here. Okay. So that will cause an issue. Why? So if all elements, note this down, that if all elements are sorted in increasing, ascending or descending order, that will be worst case of Quicksort. Why? Because we will have only one partition. There is no dividing happening. So in the case of this sorted array, in the case of the sorted array, how many times do we have to apply partition algorithm? We have to apply it n times. And remember, in the partition algorithm, we are having a loop. From I +1 to j, which is almost around order of n. This is actually order of n minus 1, but you can consider it order of n. So partition algorithm is actually taking order of n. Partition only single pass of partition algo will take order of n. Why? Because there is a for loop from I to j. If I to j have n elements, it will take order of n. Now, if we end up having only one partition, right? So we are eliminating only one element. In the second pass, this is first pass, okay? In the second pass, how many elements will we have? It's n minus 1 elements. Okay, let me try to explain it like this. If all elements are sorted, we will end up having only one partition with one less element. Okay, so 1, 2, 3, 4, 5, 6, 7. If we have a sorted array like this, once we apply the partition algorithm, we will have only one partition like this, which have n minus 1 elements. In the next pass, we will have n minus 2 elements. In the next pass, we have n minus 3 elements. So if you do the summation, the effort of the partition algorithm in the first pass is n. In the second pass is n minus 1. In the third pass is n minus 2. In the fourth pass is n minus 3. And so on. In the last pass, we have only one element, right? So if you sum these up, this will be n plus 1 by 2, which is order of n square. So this is very bad. Why? Because order of n square is too high. Even merge sort was taking order of n log n. But in case of merge sort, we were using extra space equal to the array only, right? So that was an issue there. Here we are not using any extra space, so this is in place. These kind of question can be asked whether Quicksort is in place or out place. Quicksort is in place algorithm. Remember this. But worst case time complexity of Quicksort is actually order of n square. And what is the worst case? If elements are already sorted in ascending or descending order, it doesn't matter actually. For example, what will happen if we have something like 7, 6, 5, 4, 3, 2, 1. So after this whole pass, we will have 1, 6, 5, 4, 3, 2, and 7. We will have only this partition left. After this pass, we will have 1, 6, 5, 4, 3, 2. This partition left. So again, we are having partition of size n, then n minus 1, then n minus 2. in case of descending also, descending, DSC, descending also, right? So it's order of n square in case of worst case, which is ascending or descending. Okay, remember this. Don't forget this. Worst case time complexity of Quicksort is order of n square. Now, what if we want to give a recurrence relation? RECU-RENC, recurrence relation for Quicksort. It's actually, in case of worst case scenario, it is Tn, T0, or you can say T1 plus Tn minus 1 plus n, because the partition algo is taking n and we are just reducing the input size with n minus 1. So it's n plus Tn minus 1. This is the worst case. And we have already solved this kind of recurrence relation. This kind of recurrence relation we have already solved. It's order of n square, right? It will generate an AP like this, arithmetic progression like this, okay? And it's order of n square. So you understand that at each level, we are taking this much effort, order of n effort, and we are reducing its size to 1 only. Okay, reducing its size, input size to 1 only. Worst case time complexity. Now let's talk about this best case, or you can say average case. So what is the best case or average case? Here, what's happening that if we divide the partition into exactly two parts of n by 2 and n by 2. For example, you have an array like the previous one, 45, and 45 reaches here, and you have two partition of n by 2 size here, n by 2 size here. Okay, two partitions. So our problem have reduced into two separate parts, n by 2 and n by 2. Okay, and again, if that keep on happening, this will come here. So our array will be divided into n by 4 and n by 4. This is also divided n by 4 or n by 4. These are exactly two parts. If it's near to exactly two parts, it's the same thing. Okay, if n is too large. Right? So effort at each level. Let's try to create a recurrence tree where we have n here, and we divide it into n by 2, n by 2. We divide this n by 4, n by 4, n by 4, n by 4. And we divide into n by 2 cube, which is n by 8, n by 2 cube. Right? So what will be the depth of the tree? It is n upon, till we have single element, right? Single element. It means that n raised to power k equal to 1 and k equal to log n. We have already solved this too many times. So depth will be log n. The depth of this tree will be log n. If we apply the partition algorithm and the array is split into exactly two parts, the depth will be log n. Okay. In case of log n depth, at each level, the effort is n. Here the effort is n. Okay, here the effort is n by 2, and we sum the effort, it's n only. At each level, we are applying n effort, and this effort belongs to partition algo. Okay, so we have log n levels, and at each level, the effort is n. So it's n log n. Why the effort at each level is n? Because if you combine these small inputs, right? If you combine the whole input, the partition algo will take n only, right? We are going to iterate it for n by 4, then 4 again n by 4, then 4 again n by 4, then 4 again n by 4. So the sum will be order of n only. So that's why the best time complexity in case of quicksort is n log n. Okay, n log n. It totally depends upon the partition of the array, how we are dividing the array. Okay, so let's write the algorithm. We have already written this partition step. Remember the partition step. You can write this down. After we have written the partition step, we can write quicksort. Quicksort QS. We are given an array A and I comma j. So if I equal j, we say that return A of I. Okay. Else we are getting the middle element in the partition. We haven't written anything, but we should return something here. At the end, we are going to return the middle, you can say index, which is P, right? We get the Pth position as the partition. So this is M, middle element, right? Middle means pivot element. It could be, if it's sorted, quicksort won't work. Quicksort will take order of n square. I comma j. Then we recursively we will call quicksort, and we say that A comma I comma m minus 1 quicksort A comma m plus 1 comma we will say q. Okay. So we'll keep on doing the partition algo, and for each partition, okay, if we apply the partition algo from I to j, we apply the partition algo and we get the pivot index as m. M have reached, M was P here actually. We have returned P, right? We have returned P from here. We have returned P from here. Okay. So this is that P. So then we will apply the partition algo here and here and do the quicksort. It's I to m minus 1 and m plus 1 to j. Okay. So this is quicksort. Simple. Now we will solve the quicksort questions. First, we should look for selection sort also, I think. We will solve selection sort as well as insertion sort, and try to understand selection sort, insertion sort, and bubble sort. Then we will try to understand that how we can apply these algorithms on given questions and which one is best in a given scenario. Okay, so once the sorting is done, we will look into some matrix multiplication part, and that will be the end of this divide and conquer, so that we can move to greedy algorithm, then from greedy to dynamic. Okay, so that's all for today. Thank you all for joining.